no, we're including everything.
Everything. Yes. Okay.
Go ahead.
Okay.
So Ceren will talk about the dynamical criticality.
Yes, so today I'm going to tell you about a story. I'm going to tell you a story about dynamical criticality. But before that, let me tell you very briefly about my research in all directions, and then we'll focus on this part today. So I also think about, like, other than the dynamical criticality, I think about many-body quantum chaos, also dynamical topological phases into the fermionic systems. So in this part, mostly we've been trying to put forward ways of probing quantum many-body chaos in boson mixtures and the spinor condensates. And there are also some other interesting the projects coming out there, trying to understand quantum chaos in more general settings than just like flow K driving or time-independent Hamiltonians. And in the other side, I'm interested in general this interplay between the topology, interactions, and dynamics. And one, I guess, recent work here is where I did something else like a calculation of the orbital magnetization in flow K transinsulator, also what we call anomalous trances. You can find this in the archive. Let's actually focus now on the topic of today. Okay, so when we say dynamical criticality, I have two things in mind. One of them is dynamical detection of quantum phase transitions. And with this, what I am thinking is more like we have an adiabatic quenches through the quantum phase transitions to probe the quantum phase transitions, and hence like the Kibble-Dirac mechanism, which is an established field. As an example, one could also do this with the sudden quenches. Okay, we're going to come there. And the second thing that I have in mind is emerging dynamical phases. So what I mean by these certain like phases of matter that could emerge when we do time evolution, when we drive the system out of equilibrium. Here, for example, we could have phases, dynamical phases, which corresponds to certain equilibrium phases, or could be more exotic, where we have dynamical phases where there's actually no equilibrium counterparts. So I'm going to tell you a story somewhere at the intersection of these two today. And my two main message is, I hope I'm going to be able to finish the first, and it's okay if I cannot come to the second. But the first story is that we're going to talk about this emerging prethermal regime when we suddenly quench to the vicinity of the quantum phase transition. And the second, if I have time, we're going to chat about how order could actually reveal itself with a dynamical measurement just at the lattice site. Okay, so the way that we're driving our system out of equilibrium is through a quench protocol, where we are quenching from a polarized state, which is easily preparable in quantum simulators. And then we make a measurement of an observable, 1 point observable, and this 1 point observable, most likely we choose the order parameter that we normally probe in equilibrium physics. Okay, so a paradigmatic model of quantum phase transitions is transverse field Ising model. You see here the coupling in the Z direction and transverse field. This coupling here, in most general case, could be long range, and that means could be actually power law decaying long range interactions. Yeah, so for this system, for example, magnetization is the order parameter, and we have a phase transition from ferromagnetically ordered state to paramagnetic disordered phase. Okay, and then with our order parameter magnetization, we can do time evolution exactly with this protocol and see that it starts decaying from 1 to some non-zero value. Okay, just like I'm drawing here. And then this non-zero value in the long time limit could be used to map a dynamical order profile. Okay, so that you see here with respect to transverse field, normally we expect the transition to happen at 1. And the dynamical order then shows this like really the feature that we expect from the the equilibrium order parameter. Okay. Then we can also ask the question for short range interacting transversal Ising model, which is another important model. And in this case, you should imagine the delta here being 0, first of all, right? So that's the integrable limit, and with the nearest neighbor couplings. So that's pretty straightforward model compared to this one. It's integrable. It's mappable to non-interacting fermions, as I'm going to show in a bit. And we can study that and learn more about this, the how to probe the dynamical phase transitions or other phases that could be coming up when we do this kind of measurements in this short range model, which is less studied compared to this one. But in this case, we realize that the non-equilibrium behavior becomes dramatically different. Okay, so I showed you that it starts decaying from 1 to some non-zero value for this long-range model. When we go to this nearest neighbor short-range model, the non-equilibrium magnetization basically decays like exponentially. Okay, so this is h is equal to 0.9. We're farther actually from the where we're not that too close to the critical point. And this actually this quench protocols were in detail studied. A theory was actually with the quenches was developed already in 2012 by Calabrese company. No, this is, you can see this is a dynamical order parameter, which I didn't show, but this is basically time average of the edge magnetization, C of t, for over a long time, which reveals this dynamical order, which is like, take these and then basically do it for different h, and that shows you this dynamical order profile. Okay, so back to here, then I showed like this idea, this exponential decay to 0 in the magnetization, basically persist when we introduce the non-integrability, when we break the integrability, which is this with delta parameter. And you can see that that still protects the short range property nature of it. It's just next nearest neighbor couplings, which breaks the integrability. So, and you see that there's some oscillations are introduced, but in the end, the exponential decay to 0 persists. Okay. So in fact, this behavior is not actually specific to transversal Ising model, either integrable or non-integrable, but we also see this in the other spin chains, XXZ model, XZ model here you're seeing from the Bar-Mantler paper. And I guess one common intuition comes from all these works that we see that the relaxation becomes the fastest at the critical point. Okay, so you see two plots here. One of them is from the spiral paper again, and you see the time, relaxation time becomes shorter and shorter, right? So it decays faster. And then here in this plot that I have, we're looking at the transversal Ising model, but we're looking at the decay exponent, right? And then it is actually becoming bigger and bigger. So it's the relaxation becomes fastest at the critical point. So now we have to contrast this bit of information with what we know from the adiabatic quenches or the Kibble-Zurek mechanism, where we know actually as we come close to the critical point, the relaxation time should diverge. And because that is critical slowing down. So coming from this bit of a wisdom, but we don't see this here. Okay.
Actually, do you see any finite size effects?
That's a good question. No, in these, I don't have a finite size effect, and the reason is because of the method that I'm applying. So I am staying, okay, I can explain the method later, but you can see that the time is very small, and that's the reason actually why I don't have any finite size effect. All the finite size effects are exponentially suppressed in the system size. And these are time-dependent DMRG results, not this one here, for the non-integrable. Okay, so, oh yeah, okay, and the other, I guess there's this other work where you can see this relaxation becomes the fastest at the quantum critical point, not only in spin chains, but also like in the 1D Fermi Hubbard model. that they are showing this behavior. So what is our twist? So we can make a twist to the story by introducing edges to the periodic chain. So far, I always talked about the periodic chain because that's what we look at, like when we're looking at the quantum phase transitions. But we can introduce an edge to the open chain, and we see, to the closed chain, and study this open chain transverse field Ising model. And we see that the dynamics now changes dramatically. Okay, so what happens is some exponential decay approaches to some steady state long time value, which is called quasi-stationary regime by Iglo and Ryder already in 2011 when they first realized actually this. So you see a plot from their paper, right? So this is the a quench from a polarized state to h is equal to 0.5, while in the deep in the ordered phase or quenching too. And you're seeing here curves actually representing local magnetizations at different probe sites, ranging from 16 to 128 or so. And you see some exponential decay starts and then approaches this quasi-stationary regime. In fact, they also show in this work that that approach has to be power law. Okay, we're going to talk about that power law in a bit. We can try to understand why this is happening when we add the edges, what changes actually so that a quasi-stationary regime appears with a heuristic argument. Okay, so here's our chain. Okay, and if you think about, we're making this asymmetric measurement with respect to the symmetry center of the chain, which is the center of the chain. We can see with a quench, we excite the system and create this quasi-particles. In particular, if we're sticking with the integrable picture, we create quasi-particles, and they start moving to opposite directions. One of them starts moving to the farther edge, and the other one actually starts moving to the closest edge, and then reflects back and visits exactly the same spot in my time evolution. Some interference effects appears here because of that reflection from the closest edge and the asymmetric measurement, and this actually stabilizes this quasi-stationary regime. So while we have this nice heuristic argument, I will show you in a bit that mathematically, to explain the origin of this quasi-stationary regime, we need to have zero modes. So what do I mean with zero modes? To explain all of these things, we have to map the transfer field Ising model to free fermions, specifically the Kitaev chain. Okay, so let me just quickly tell you, Kitaev chain is simplest topological superconductor. You see the pairing terms here appearing, which gives the superconductor part to it, and it has basically a topological phase. In the spin part corresponds to the ordered phase, and the non-topological trivial phase, which corresponds to the disordered phase in the spin chain. Okay, so we map this through our mapping operators here. Okay, and you can see the mapping is this in 1D is an exact duality that there, exact mapping. But basically, you can see that the spin operators become like non-local in the fermionic picture. Okay, so you see, yes. So okay, and from that non-locality, you can see if I want to measure actually the a spin at the bulk, say, I'm bringing a string of operators in the fermionic chain. This is what you can see here. This is a string of operators that comes. So it's actually not that straightforward. It's a little bit tricky, but this is really the only way to we can understand an analytical calculation coming up. Yes.
Okay, so just to slow down a bit, if I set h to 0 in this block in the Hamiltonian above, why do I not recover the kind of the fermion version of the model? Then it's just a classical.
So yeah, if you take h is equal to 0, this is actually classical limit.
Right, but why the lower equation there's still like the C dagger.
Okay, because I apply the rotated mapping here. This mapping is not the standard mapping. I want to keep using this kind of mapping to connect basically the local magnetization in the Z direction to the string of operators here in the fermionic picture.
So it's just the Jordan.
It's Jordan-Wigner transformation. exactly. It is just Jordan Wigner transformation, but it's in rotated. You can see that. Yeah.
So the rotation does
Yes, rotation brings that part there. Yeah. Okay, so I have two methods here that I used. One of them is I invoke cluster theorem. Cluster theorem, here you see the statement for this. And when we write the cluster theorem, of course, it brings some limitations, but let me just not go over that right now. We can calculate the 1-point observables in terms of the 2-point correlators, okay? Which is easier to calculate a 2-point correlator in this case, okay? And the second method is Al-Asi and Young from 1952, where he actually defined the local magnetization with respect to the single particle ground state and single particle excited state. Okay, so this is another method that we could use. But in all of the calculations, the results that I'm going to show you in the rest of the talk, I'm using cluster theorem method. Okay. All right, so let's talk about this briefly. To show that zero modes are important, we have to have zero modes. To see the quasi-stationary regime, we use the second method that I mentioned. And let's do this very quickly for the edge, because this is really the most straightforward one that we could understand, right? So we can write down the edge magnetization, C1 of T, right? In terms of the single particle energies and single particle eigenstate elements coming up, okay? For different cases, I'm not gonna explain further, but from here, we can immediately see the energy condition that requires to get a non-zero value for the edge magnetization when we go to the long time limit, T infinity. And that is actually that EQ has to be 0 for that. So then we see from very simple demonstration that we have to have zero modes in order to have a non-zero value in the infinite time, which is our quasi-stationary value. So we can go ahead and actually plot this with respect to H, right? And that gives us the form as 1 minus H squared. So this is the quasi-stationary value for each H. And now you can also see the non-analyticity coming immediately with this H magnetization, because this is the ordered phase. We have this nice 1 minus H squared dynamical order profile. And then when we pass through the phase transition at 1, we have 0. So it's a non-analyticity basically probe. We can hope to do this for bulk points, bulk probes, but it is going to be hard, right? So let's just look at, for example, the second one. Let me just sketch very quickly, and then if you're interested, we can also discuss maybe further into the bulk. But for the second one, you can see the string of operators coming already for the second measurement site, right? Coming, the first part is coming. I put this in a suggestive format here because we have to go to the Majorana basis to calculate. So these are Majorana operators or auxiliary operators, if you like. And from here, I basically write down this as an antisymmetric matrix and take the Pfaffian of it. I use the Wick's theorem basically to put this in a correlator in terms of correlators, and then just like putting stuff on the rug here, but basically just point to that like this can be written as in a factorized way, and depending on the different parts of the fermionic chain. From here, let me just tell you what energy condition comes out, because I really don't want to get into that mess here. Energy condition comes in form of these plus minus, some combination of this 3 different energies has to be 0 for us to have some non-zero value in the infinite time limit, okay? And assuming we have non-degenerate single particle spectrum, which is the case for transversal Ising model, then this actually requires that all my energies has to be 0 separately. And then that again tells me that I need to have 0 modes in the system supported. We can look at this like in the numerics. This is the 6th site. You're seeing like the dynamical profile at a local 6, the site at 6th site, and for different system sizes, and some non-analyticity coming up again, and it's getting sharper with increasing system size. And one could actually numerically show this for other points further into the bulk as well. So basically, not only edge spin seeing the 0 modes, but any bulk spin is susceptible to the 0 modes. Okay. and gives us non-analyticity at the critical point. All right, I don't know how much time I have, maybe 10 minutes? 5, total of 10 minutes. Okay, I didn't have any questions, so maybe I'll try to finish up. Okay, so let me now tell you about the physics near the quantum phase transitions. Now, I am interested, so far I told you about the quenching well in the ordered phase, deep in the ordered phase, but now I'm interested in quenching to the vicinity of the quantum phase transition. In this case, we have 3 temporal regimes appearing. Okay, so the first temporal regime is decay regime, which we already know that's going to happen. But I guess maybe an interesting thing here, the decay actually is not exponential anymore, but it's really just power law decay. Okay, and the form of it is t to the minus 3/2, and this is not specific to the edge, but also it happens in all other bulk sites as well. And then we have other known part that we already talked about a lot, quasi-stationary regime. But then there is a new new regime comes up, which cannot be explained either with the decay regime or the quasi-stationary regime, which I'm going to call right now prethermal regime. I'm going to try to explain to you why it is actually critically prethermal regime. Here you can see the panels, and then I try to roughly put some timescales here. TPT is the onset of the prethermal regime, and the TQS is the onset of the quasi-stationary regime. Right, and this is for the edge. The blue part is the numerics, and then the red dotted line is our analytics. Yeah, which is basically when we derive the equation for the edge, it comes out as a series equation in terms of Narayana polynomials, and I'm here. Just note that here the series is a series in T and also the H, the transverse field. All right, so it's not specific to the edge. We can numerically calculate the other parts, and we can see this nice prethermal regime coming up here. There's some sort of ramp behavior, dip and ramp. Okay, now we're going to try to characterize that. To characterize that, we have to expand around the critical point. And we do this expansion right here. Note that I did some change of variables, and now we define this like new variable coming from the expansion, which I'm calling delta CR, function of T and H. Okay, let's visualize what this is. The black part is the analytics that I just showed you from the series calculation. Okay, and then the blue part is the numerics. Since I don't have much time, I'm just gonna go here. I'm not gonna explain why this kind of slight deviation happens here, but pretty much overall the match is really good. And then we do this, okay? We do this derivation here and comes out some terms here. Maybe we can try to understand the terms, a few terms. So the first one is H tilde over 2, which is basically a constant term, which basically gives us the early time part, okay? And then some oscillations around it, because some Bessel function comes out there, okay? So these oscillations big initially, but then it becomes smaller and smaller, which is exactly what we expect in the Bessel function. And now we are having this interesting series coming up, okay? And that actually gives us the overall shape of this ramp approach to quasi-stationary regime. Okay, this is actually enough for us. We don't have to even go further. Let me actually put down now like this red curve here is specifically this part, the constant part, and then the series. I'm getting rid of this Bessel part because I know that's not universal. So because I'm trying to like find the universal parts of it, and the universal parts of it is really this red line. We can try to understand the forms coming in this, but since I don't have much time, I'm not gonna go further into details here. Basically, we can look at like the leading order terms coming from the series and see, like, try to have a better sense of it. But for now, we're just moving so that I can show you how data for different sites and initial states collapse on each other when rescaled according to some arbitrary time point. which is rescaling is shown here, that you can see from the y-axis that I am rescaling over to some time point. And data actually, the overall collapses to reveal this like pre-terminal ramp nicely. We don't have a collapse here, which is expected because this is the part where some Bessel functions coming, non-universal corrections, and most likely it is coming like for different sites differently, which I'm not interested. I'm only interested really this like the constant part and the series part that's bringing us. Okay, and the last thing that I'm gonna tell you, what can we learn from this function? Okay, so you see H tilde and then inside H tilde T, okay? So that's a homogeneous function. And what we can learn physically from that is actually how this duration of the pre-terminal ramp is related to the single particle energy gap, okay? And for this, let me start first like showing you this delta T, which is the duration of the pre-terminal ramp, quasi-stationary onset time minus pre-terminal onset time, right? And now, before I hand-wavingly define these onsets of times, right? But now, giving this function, I can define these times more precisely. And you can see that these are actually coming from the function. When I am choosing my, the onset of the pre-terminal regime, I know that I am somewhere in the early part, so that only this part contributes. And then the quasi-stationary regime, I have to actually go further into this part. Okay, and from here, when we basically substitute and do the calculation, we end up having the pre-terminal regime inversely proportional to the single particle energy gap. So that means as I come close to the critical point, the pre-terminal duration is going to get bigger and bigger. It's going to diverge. So this is exactly critically pre-terminal regime. And because of the nice match with the rest of the sites and different initial state, this suggests that it's a universal critical pre-terminal regime. Okay, so I think I am actually done. So I'm not going to go further into this further test of the universality or the scaling near the critical point, which is very interesting because a nonlinear scaling comes out exactly because of this pre-terminal ramp. All right, we're not going any of these things. And then we also don't talk about these things. Yes, I'm done. Thank you.
Get an update on those next year.
I wanted to ask you, so you said one of the motivation to study this effect compared to the previous studies was to introduce the boundaries.
Yeah, so in all those works, it's periodic boundary conditions. And that's why it exponentially decays to zero, the non-equilibrium dynamics. What we do is we cut open it with the edges introduced. Now we can actually see that relaxation diverges near the critical point, which was missing in the previous picture because they were seeing the relaxation should be fastest around and at the critical point.
But it is precisely because of the boundaries you have these localized
Yes,
zero energy states for the
so the quasi-stationary regime, definitely the origin of its zero modes mathematically, that is very clear from our little proofs. But the reason of the pre-terminal regime, that's the gap, the single particle energy gap. So, and that's because, you know, we have a well-defined gap to gapless phase transition there from ordered to disordered phase. With the boundaries, yes. I mean, phase transition is defined regardless of the boundaries, but the measurement is best done, I think, with the boundaries. In that sense, if you want to catch that, like the divergence of the relaxation near the critical point, critical slowing down, if you want to probe that, we have to have boundaries.
Can it be related to that? I mean, at some point you were saying it's not a finite size effect.
Yes,
but
it's
at
not
the
a
same
finite.
time, like, if you simulate the entire system with periodic boundary conditions, it doesn't matter how large the system is.
Not necessarily. In periodic boundary conditions, you're going to eventually actually see the finite size effect appearing in time. And that's because you can think that in time, the correlations of different sites are going to evolve and they're going to start seeing each
Right, but
other.
if I make the box larger and larger and larger, and I keep like periodic boundaries.
Sure, you can do finite size system analysis, but like eventually with the periodic boundary conditions, you will actually see, exponentially decaying to zero. But with these, the results don't have finite size effects. At least the finite size effects are suppressed in the system size. You can see that, for example, I mean, I guess the best evidence of this is our
But somehow like trying to maybe I missed it, like I'm trying to wrap my head around like how like kind of the boundary effects can matter if it's not a finite size effect.
So you can think this in a semi-infinite strip. Okay, so you do need to have a boundary. Or one could do is actually you can take a periodic boundary conditions, but put like a domain wall in between. You need to have this kind of edge appearing so that you can stop going like this, stop that interrupting that exponential decay to zero and stabilize this quasi-stationary regime and probe all these things that we've been talking. For example, this orange line here is in thermodynamics, in thermodynamic limit, basically. There is no like system size information there. That you have one edge, but the other edge is in the thermodynamic limit. And these numerical results here is basically there is no like the finite size effects are exponentially suppressed in the system size, which is 2000 spins. That's why I can go to very further into the time info.
Is there any interesting feature of the correlation length of this prethermal regime?
Correlation length of the I guess if you have the 2-point correlators, that's a good question because here I am totally focusing on the 1-point observables, right? One has to calculate the 2-point observables for that, but yes, that's a good question.
Thanks, Sharon. There's pizza. Shop to be back in 12:45. Just. Well,